Hello everyone. So going to start very important research paper. Today I'm going to start this paper, enhancing the educational model using mixed reality technologies with MetaQuest 3, a usability analysis using IBM CSUQ. Okay, so be prepared. Going to start reading it while listening. You have to be careful while okay. So going to start it. First I will do full screen. Okay, now starting it.
Received the 2005th of February 2025. Accepted the 2006th of March 2025.
1 minute. What I can do? I can check out whether it's recording or not recording. No source selected. I think it's recording. Okay, fine. Thanks.
Date of publication the 28th of March 2025. Date of current version the 7th of April 2025. Digital Object Identifier 10.1109. Access. Enhancing the educational model using mixed reality technologies with MetaQuest 3.
Yeah.
A usability analysis using IBM-CSUQ. Santiago Criollo C1. Andrea Guerrero Arias 2. Agariadne Duingo Samala 3. Unifa Miftashul Ari 4. And Sergio Lujan Mora Fiv 1 Carrera de Ingeniería en Ciberseguridad.
Starting from
Abstract in today's education landscape. There is a lack of effective digital tools for hands-on teaching of PC and smartphone hardware assembly, especially in environments where physical resources are limited. This challenge is critical, because practical learning in hardware is essential for developing technical skills in engineering students and related fields. Traditional alternatives such as simulators or online tutorials have not managed to provide an immersive and efficient learning experience. To address this need, Build 3D was developed, a mixed reality application designed for learning PC and smartphone hardware assembly, experienced through the MetaQuest 3 headset. The use of MR in an educational context is a topic of considerable debate, given the necessity for a comprehensive analysis of its potential advantages and disadvantages. This research proposes an evaluation of Build 3D's usability using the Computer System Usability Questionnaire, focusing on three key dimensions: interface quality, information quality, and system usability. The results indicate high user satisfaction, with interface quality rated the highest, followed by information quality and system usability. These findings suggest that this application provides an immersive and effective educational experience, minimizing cognitive load without compromising the quality of practical learning. The implications of this solution point to an improvement in hands-on hardware teaching through MR technologies, offering a viable and scalable alternative in educational environments with limited access to physical labs. Finally, this facilitates autonomous and motivating acquisition of technical skills for students. Index terms: mixed reality, PC hardware education, usability evaluation, IBM-CSUQ, user satisfaction, MetaQuest.
Yeah.
First introduction in recent decades. The evolution of digital technologies has radically transformed nearly every aspect of society, including entertainment, communication, healthcare, and especially. The associate editor coordinating the review of this manuscript. Approving it for publication was Martin Reislein. Education. As technological tools have become more accessible and advanced, their integration into educational processes has created new opportunities to enhance the learning experience, making it more interactive, personalized, and immersive. Among these technologies, mixed reality has emerged as one of the most promising innovations, combining the benefits of virtual reality and augmented reality to create environments where the physical and virtual worlds merge, allowing users to interact with both in real time. Over the past few years, the incorporation of digital technologies in education has accelerated significantly. The advent of online learning platforms such as Moodle and Blackboard marked the beginning of large-scale digital learning. These platforms provided students with access to educational materials and enabled remote interaction with teachers and classmates, democratizing access to education globally. Later, with the rise of mobile devices, learning became even more accessible through educational applications and the use of tools such as massive open online courses.
Yeah.
However, although these technologies improved access to information and learning flexibility, challenges remained in terms of practical interaction and personalization of the educational experience, especially in fields that require hands-on approach, such as engineering, medicine, and applied sciences. MR is a technology that combines elements of VR and AR. VR creates fully immersive environments that transport users to digitally generated worlds.
1 minute. Sorry for interpreting, but I want to tell that MR is not Mr. That she is saying MR Mr. is not Mr. It's mixed reality. Okay. MR means mixed reality. Okay.
Meanwhile, AR overlays digital information onto the real physical environment, allowing users to view and interact with virtual elements in their physical space. MR, therefore, merges these two technologies, enabling users to simultaneously interact with virtual and physical objects in a unified environment. The evolution of MR has been driven by advances in graphics processing capacity, the development of lighter, more ergonomic devices, and improvements in natural interaction systems, such as eye tracking, gesture recognition, and voice commands. Devices like the Microsoft HoloLens and Meta Quest 3 represent some of the most advanced developments in MR, allowing users to experience a world where the physical and digital blend seamlessly. The application of MR in engineering education holds significant potential, yet it remains relatively underexplored compared to its use in fields like medicine, fundamental sciences, and sports. As MR has matured, its use has expanded across various sectors. In industry, for example, it is used to simulate complex processes, train workers in hazardous tasks, or perform remote maintenance with real-time visual guides. In medicine, MR has been employed in surgery planning and medical student training, allowing them to practice complex procedures in highly realistic simulations without putting patient lives at risk. Another key application area has been entertainment, where MR is used to create immersive experiences in video games, movies, and interactive events. These experiences are not only entertaining but can also have educational applications, allowing users to learn through simulation and interaction with previously inaccessible content. In education, MR has proven to be a powerful tool for transforming and innovating learning. MR enables students to experience abstract concepts in tangible ways, which is especially beneficial in areas such as engineering, natural sciences, and medicine. For example, in teaching chemistry, MR can allow students to manipulate subatomic particles in a virtual environment, helping them understand phenomena that would otherwise be difficult to visualize. One of MR's main advantages in education is its ability to create immersive and personalized learning environments. Through interaction with objects, students can learn at their own pace, repeating procedures or experiments as many times as necessary without the limitations of physical resources. The value of MR in engineering extends beyond traditional instructional methods by enabling students to interact with virtual models of complex equipment. This approach not only reduces the need for physical components, but also minimizes the risk of equipment damage, a common issue in hardware labs, where students handle sensitive, expensive devices. By reducing the risk of damage, MR also fosters a more confident, exploratory approach to learning, as students can experiment freely without fear of breaking real components. Additionally, MR enables a more practical approach to learning, something difficult to achieve with other educational technologies. The immersive environments created by MR not only enhance knowledge retention, but also increase student motivation, as they are more engaged when actively interacting with content. In this context, the Build 3D MR application, developed for the Meta Quest 3 headset, represents an innovative solution for learning PC and smartphone hardware assembly. Build 3D allows students to interact with three-dimensional models of hardware components in a mixed environment, combining virtual objects with the physical environment. Students can assemble and disassemble hardware without the need for costly equipment or physical labs. Using Build 3D not only reduces dependence on physical resources, but also offers the possibility of repeating complex procedures as many times as necessary, significantly improving the acquisition of practical skills. Furthermore, the ability to work in a safe and controlled environment minimizes the risk of damaging expensive components,
Yeah,
a common concern in traditional hardware labs.
yeah.
These advantages, there is a pressing need to assess the usability of MR tools like Build 3D in educational settings to ensure they effectively support meaningful learning outcomes. The usability of such applications is crucial, as a poorly designed interface or overly complex interactions could hinder students' understanding and reduce engagement, ultimately impacting their ability to successfully learn and apply complex assembly and operation skills. Therefore, this research aims to analyze the usability perceived by students when using Build 3D as a support tool for teaching the operation and assembly of technological equipment, seeking to determine if it enables a productive and immersive learning experience. This application was specifically developed to motivate students in acquiring the skills necessary to understand the operation and components of PC and smartphone hardware. The objectives of this research were: Objective 1, analyze the usability perception experienced by students when using Build 3D as an educational support tool. Objective 2, identify the perceived utility of Build 3D as an educational support tool. To measure the effectiveness of learning to use Build 3D, it is essential to evaluate its usability from the student's perspective. In this study, the Computer System Usability Questionnaire was used, a widely accepted standard for measuring user satisfaction in terms of three key dimensions: interface
Windows
quality,
quality,
information
performance
quality,
quality,
and
system
system
is the
usability.
yeah.
These dimensions provide a comprehensive view of the user experience when interacting with the application and allow areas for improvement to be identified. The results of the Build 3D usability evaluation were highly positive, indicating that the system meets the functional requirements to facilitate the intended learning. In this section, the reader is introduced to the research topic. The following sections of this paper are organized as follows. Section 2 reviews the application of MR technology in education. Section 2 details the research methodology employed. Section 4 presents the research findings. Section 5 discusses these results in depth. Section 6 outlines the study's conclusions, and Section 7 suggests directions for future research. Second, related work. In recent years, MR technology has gained ground across various sectors, particularly in education. Mr. allows students to interact with both virtual objects and their physical environment, creating unique opportunities for experiential learning. From elementary to higher education, this technology has been applied to teach complex concepts in an interactive and immersive manner. As Mr. devices, such as the Microsoft HoloLens and Meta Quest headsets, have evolved and become more accessible, their use in educational settings has significantly increased. Several studies have shown that Mr. can improve knowledge retention, increase motivation, and facilitate the understanding of abstract concepts. Immersion transforms passive learning into active engagement, deeply involving students in the content. Furthermore, the ability to manipulate virtual objects in real time allows a more tangible understanding of the topics being studied, which is especially useful in disciplines such as science, engineering, and medicine. Mr. demonstrated that the portability of devices positively influences perceived ease of use and utility for hands-on learning and crime scene analysis. Likewise, Mr. Technology has been successfully applied to innovate the teaching of engineering subjects. The research conducted by Sahin et al. Enables students to visualize connections between wireless nodes, antenna radiation, patterns, and data performance in wireless networks.
Yeah.
These immersive environments allowed testing different configurations and analyzing the behavior of communication systems in real time without the need for physical laboratories. This type of practice not only reinforces theoretical concepts but also minimizes the risk of costly errors in physical environments. In this context, Wu et al. Explore how Mr. Technology can help bridge the skills gap in the construction and engineering industry by facilitating the learning of tacit knowledge and improving the transition of university students into the workplace. Through a case study in a timber structure construction laboratory, the performance of student groups using Mr. Visualization technology was compared to a control group working with traditional paper drawings. Preliminary results suggest that Mr. enhances students' understanding of design and the skills necessary for constructing structures, providing a basis for future research in this area. Martin Gutierrez et al. Analyzed the validation and usability of a Mr. application designed to develop spatial skills in first-year engineering students. The results were compared between students using head-mounted hardware versus PC monitors. The findings confirm the validity of the training and suggest improvements in the interface and educational materials, highlighting the effectiveness of Mr. in improving academic performance. Tomcore discuss how Mr. applications personalize engineering education, particularly in geometric visualization. Students with visualization problems benefited from Mr. technologies that allow them to observe and manipulate 3D models. Mental rotation tests, conducted before and after training, showed improvements in visualization skills, suggesting that a background in video games influences the level of benefit obtained from Mr. technologies. Richard et al. Explore the use of Mr.-based games in engineering education, proposing a diversified and experience-oriented learning environment. The design of these games enables the integration and practice of technical and methodological topics in a collaborative and applied learning setting. Aziz et al. Developed an MRI and VR system to enhance education and training in engineering assembly processes. The system, tested with university students, showed improvements in comprehension and psychomotor skills, demonstrating that MRI can be adopted as an effective learning method for training and maintenance and assembly of machine parts. Muller et al. Present a collaborative learning space that combines real, virtual, and remote tools, facilitating collaborative experimentation in engineering education. In addition, they discuss concepts related to the use of RM technology and identify future research to improve remote collaborative work in engineering education. Suhail et al. Systematically review the use of Mr. in engineering education, highlighting its educational impact and identifying areas for improvement. Their findings show that the use of this technology can enhance visualization, interaction, and student motivation in disciplines such as civil and mechanical engineering. Although its adoption in other areas is limited, they recommend addressing technical challenges and improving curricular integration. To maximize the educational benefits of Mr. Solutions offer significant benefits in education, such as increased motivation for learning and self-learning through direct interaction with virtual components, surpassing traditional teaching approaches. Furthermore, Mr. enhances the development of spatial and psychomotor skills by allowing students to visualize and manipulate 3D models. It has also been demonstrated that the use of Mr. as an educational aid increases student engagement and participation compared to traditional methods due to its more interactive and immersive experiences. However, Mr. Solutions have limitations, including the high cost of hardware, technical challenges in system integration, and potential physical discomfort due to prolonged use of Mr. glasses.
Yeah.
Traditional teaching is more affordable and easier to implement, outperforming Mr. in terms of cost and logistical simplicity.
Yes.
Additionally, it does not require advanced technical knowledge, nor does it present physical discomfort issues such as dizziness or eye strain, which are common in Mr. environments.
Yeah.
However, compared to Mr., traditional methods lack the immersion and interactivity needed to develop complex spatial skills or simulate advanced assembly scenarios, which may limit student engagement and long-term knowledge retention. Third methodology, an Mr. application called Build 3D, was designed to teach topics related to PC and smartphone hardware. This application effectively addresses pedagogical needs by providing a practical, dynamic, safe, and accessible learning environment that enhances students' theoretical and practical understanding. A Build 3D design. 1. Design process. The project was born from the idea of building a tool focused on learning about the components and assembly of hardware, such as a computer and a smartphone, using MR technology. To achieve this goal, two challenges had to be overcome with innovation and creativity. The first challenge was the assembly process for the elements, and the second was designing an interface that provides an optimal user experience. The application enables users to take components and assemble them correctly with natural interactions, meaning minimal friction and as closely resembling real-life actions as possible. The natural approach allows users to manipulate objects, position them, release them, or rearrange them using hand gestures like grabbing and releasing. To accomplish this, customized software and code were utilized, leveraging the integrated cameras and meta, separation, opposition, figure 1, finger position for interacting with 3D objects in MR environments, Quest 3 to detect hand silhouettes, finger positions, curvature, flexion, spacing between fingers, and opposition. Figure 1 shows the 4 positions that fingers can assume, designed to create a MR application suitable for its intended use and functionality. Curvature detects how curled the fingers are based on their joints. Flexion detects the angle at which the knuckles bend toward the palm. Spacing relative to other fingers identifies when adjacent fingers are separated, forming an angle. Finally, opposition detects the proximity of a fingertip to the thumb, applied specifically to the index, middle, ring, and little fingers. 2 main points are proposed for MR software development. 3D objects. These are placed in the scene to prompt an action based on familiar real-world object usage. For example, using a red button indicates to the user that interacting with this 3D element requires pressing it, after which an expected outcome will occur. This is especially important for novice MR users. Spatial text. The application includes a feature that displays detailed information about each component in text form. The user can handle the text as a 3D object to read it, but upon releasing it, it might be positioned at an awkward angle or even rendered invisible. To address this issue, a text tracking system was implemented, allowing the text to track both the object and the user's position. 2. Requirements. To design a MR application for the MetaQuest 3, it is essential to consider a series of design requirements that ensure an immersive, intuitive, and efficient experience for the user. The development focused on both the educational perspective and the user experience. As shown in Table 1, several requirements must be met for the design of Table 1. Design requirements for application usability. The MR application. These include integration of the physical and virtual environment, an intuitive user interface, optimization, comfort, ergonomics, and accessibility. In addition, Table 2 presents the technological tools used, and Table 3 details the specific libraries and dependencies used for the design of Build 3D. 3. Development methodology. The Scrum methodology was employed due to the project's nature, which required incremental progress to test interactions during the development phase. 6 iterations were defined over 6 weeks, given the team's knowledge and proficiency with the technologies used. 4. Build 3D application visualization. Figure 2 provides a detailed visualization of the disassembly process of a PC and a smartphone. The background displayed in these figures is an example of the ability to use MR ubiquitously. This academic support can be used in the classroom or outside the classroom. In these figures, Build 3D uses MR to show key internal elements such as the battery, the motherboard, the camera module, or the haptic engine, among others. Detailed segmentation allows users to see each component in its physical context, facilitating interactive learning about PC and smartphone hardware. Figure 2 shows that users can interact directly with device components, simulating actions such as removing the motherboard. This suggests that the application promotes a hands-on, immersive approach, which can improve information retention and motivation in learning. Direct manipulation of components. In MR Space represents a significant advance over traditional teaching methods, such as textbooks or 2D simulations. In each scene, floating information panels are used to explain the hardware components. The texts provide technical descriptions of the purpose and characteristics of each component. This accessible presentation allows students to learn at their own pace, providing a personalized educational experience. The application is scalable in terms of the types of devices that can be disassembled, suggesting that it can be extended to other hardware or electronic devices, which would provide versatility for different training areas. Additionally, as seen in Figure 2, there is a mechanism that can be pressed to switch between the visualization of a smartphone and a PC, highlighting a key feature in the design of Build 3D, which is its ability to teach various types of hardware technology. This shows that the application can be adjusted to different levels of knowledge, covering both simple components and more complex systems like those in a PC. 5. Build 3D usage and sequence. The sequence diagram for using Build 3D is outlined as follows. The components info-follow-component.cs, initialization, and follow component and phase camera ensure that each component's information follows its respective object in a 3D environment, maintaining the front face of the text always visible to the player. After initialization, the main camera is verified and assigned to track the player's view. During execution, the information text is adjusted in real time to remain aligned to the front of the Table 2. Technological tools. Player, ensuring that the text is always legible and visible. The mainboard verification.cs, mainboard placement, and mainboard removal. components guarantee that the mainboard, in the simulation, is correctly positioned before. Table 3. Libraries and dependencies used. Table 3. Libraries and dependencies used. Figure 2. Handling hardware components in Build 3D, allowing the installation of its internal components. This ensures that the assembly process continues only if the mainboard is properly installed. The components show-info-manager.cs, start and setup, deactivating information, activating information, toggling information, provide an overview of the Figure 3. Build 3D user activity diagram, methods and their effects on the assembly flow, which helps to understand the process and dependencies between the components and the mainboard. These components prepare the initial state of the system, activate the information of all components, making the details visible to the user. Finally, the information is activated when the player presses the Information button. The components snap-manager.ces, start and setup, component placement with mainboard requirement, and updating all slots, enable assembly, and help to understand the process and dependencies between components and the mainboard. They also manage the assembly of components that depend on the mainboard. In case the assembly is not yet complete, a warning message is displayed. You must attach the mainboard before attaching this component. In addition, it serves to deactivate all slots for objects that require the mainboard. The show-info-manager.cs, start and setup, deactivating information, activating information, toggling information. Components manage the assembly of components, ensuring that the mainboard is in place before allowing the installation of other components. They also manage the display of detailed component information, allowing information to be enabled, disabled, or toggled based on user actions. The show hologram-hint.cs, start and setup, object enters zone, object stays in zone, object exits zone. Components provide a holographic visual reference to guide the user in the correct assembly of PC components. During interaction, the holograms are activated when components enter the detection zone, verifying if they are correctly aligned, and deactivates the hologram when components exit the detection zone. The system also handles collision validation and ensures that components are mounted in the correct location. The use of all these components allows the application to be simple to use, and students have no extra cognitive load when using Build 3D to support their education. Figures 3 and 4 show the sequence and usage diagrams of Build 3D, in which the simple use of this educational application can be observed. Build 3D usability evaluation. Unlike similar initiatives in the current literature, this research did not focus solely on the design aspects and results of using Build 3D. Instead, the objective of this study is to evaluate the usability of Build 3D. To achieve this, the IBM-CSUQ tool, which measures user satisfaction regarding the use of Build 3D. The IBM-CSUQ is an established tool for assessing the quality and effectiveness of interactive systems from the user's perspective. Its application in this study provides detailed insight into how users perceive the usability and usefulness of the application. 1. Participants. This research involved the participation of students from a higher education institution. All students agreed to informed consent provided through a web form. Participants were selected through convenient sampling. Of the 50 participants, 22 were women and 28 were men. 2. Task. The experiment began with an introduction to using the Build 3D application. Participants had the opportunity to ask, Figure 4, Build 3D sequence diagram, questions and provide feedback and recommendations on the designed application. Students used Build 3D. Each participant spent approximately 10 minutes assembling the PC and 10 minutes assembling the smartphone. Students completed the IBM-CSUQ questionnaire. The information gathered helped assess their perception of the usability of Mr. Technology as a support tool in higher education. Additionally, students responded to a survey designed to identify the application's usefulness and their recommendation for its use. These data can be valuable for educators and educational institutions seeking to incorporate MR to innovate traditional methodologies and adequately address current challenges in the learning process. 3. Usability analysis. To evaluate the usability of Build 3D, a survey based on the IBM-CSUQ tool was used, employing a 7-point Likert scale. This questionnaire consists of 19 questions designed to measure user satisfaction with the developed application. The survey aims to gather data on various aspects, such as system usability, the quality of information provided, interface quality, and an overall assessment of the application and its ease of use. The questionnaire questions are presented below. Question SISUs. Q1 overall, I am satisfied with how easy it is to use this system. Q2, it is simple to use the system. Q3, I can effectively complete my work using this system. Q4, I am able to complete my work quickly using this system. 5 Guatemalan quetzals, I am able to efficiently complete my work using this system. 6 Guatemalan quetzals, I feel comfortable using this system. 7 Guatemalan quetzals, it was easy to learn to use this system. 8 Guatemalan quetzals, I believe I became productive quickly using the system. Questions info queal. 9 Guatemalan quetzals, the system gives error messages that clearly tell me how to fix problems. 10 Guatemalan quetzals, whenever I make a mistake using the system, I recover easily and quickly. 11 Guatemalan quetzals, the information provided with the system is clear. 12 Guatemalan quetzals, it is easy to find the information I need. 13 Guatemalan quetzals, the information provided with the system is easy to understand. 14 Guatemalan quetzals, the information is effective in helping me complete my work. 15 Guatemalan quetzals, the organization of information on the system screens is clear.
Yeah.
Questions interquile. 16 Guatemalan quetzals, the interface of this system is pleasant. 17 Guatemalan quetzals, I like using the interface of this system. 18 Guatemalan quetzals, this system has all the functions and capabilities I expect it to have. Question overall. 19 Guatemalan quetzals, overall I am satisfied with the system. 4. Perceived usefulness analysis. When designing an educational application, it is not only crucial for it to function effectively, but also for users to consider it potentially useful as a support in their educational process. For this reason, a survey was used to measure the perceived usefulness of Build 3D as a complementary tool in teaching PC and smartphone hardware. The questions used in the survey, based on the research by Criollo et al., are as follows. Q&A: do you think this application is applicable in classrooms to motivate learning about PC hardware and smartphone? QB: do you think this application gives students an interesting insight into the parts of a PC and smartphone? QC: would you use this application in your classroom? QD: do you think that using this application improves your learning? QE: do you consider this application as an effective tool for guided learning in class? QF: would you recommend this application as an educational tool in the classroom? This survey also includes a multiple choice question. After using the application, participants were asked to choose a word that describes their perception of its use from the following options: useful, entertaining, easy to use, friendly, motivating, intuitive, or prefer not to answer. Fourth results. A. Usability analysis. Table 4 presents the mean, standard deviation, and median results for the 4 categories of the IBM-CSUQ tool. This table provides insight into the central tendency and variability of responses across different usability dimensions. Table 5 displays the maximum, average, and minimum values obtained from the usability analysis tool. These data points help to identify the range of user perceptions regarding the mixed reality application for PC and smartphone hardware practice, using the MetaQuest 3 headset. Figure 5 graphically illustrates the results from the previous tables, facilitating a comparative visualization of the top, average, and bottom values in each usability category. Additionally, figures 6 and 7 respectively show the responses of the participants, grouped by gender. These charts allow for an analysis of how each group experiences the usability of the Build 3D application. Additionally, potential differences between genders regarding the perception of usability as an educational support tool could be crucial for a comprehensive interpretation of the results.
Yeah.
Table 4. Mean, standard deviation, and median survey across all participants. Table 5. Top, average, bottom, and minimum values obtained with the usability analysis tool. Figure 5. General results of the IBM-CSUQ survey.
Okay.
These visualizations contribute to a deeper understanding of the data, highlighting key aspects of the user experience in the educational context with emerging technologies. Figure 6. Response of participants in the IBM-CSUQ survey. Figure 7. Response of participants in the IBM-CSUQ survey. B. Perceived usefulness analysis. Figures 8 and 9 show all participants' perceptions regarding the usefulness and use of Build 3D as support within the educational model. Additionally, Figure 9 presents the words chosen by students to describe the application. Most students perceive the application as useful and easy to use, which is a positive indicator that the tool is fulfilling its educational purpose.
Yeah.
This could suggest that Build 3D is effectively facilitating learning about PC and smartphone hardware.
That's cool.
Fifth discussion. A. Objective 1. The IBM-CSUQ tool is a widely used and recognized tool in the field of usability. In this research, it is demonstrated to be Figure 8. Answer to questions Q&A, QB, QC, QD, QE, and QF. Figure 9. Answer to questions Q&A, QB, QC, QD, QE, and QF. Figure 10. Using words to describe the application. Effective, easy to use, comprehensive in scope, standardized, and adaptable. The usability study revealed a positive result. In the IBM-CSUQ survey, most participants responded agree or strongly agree to the questions posed. This can be seen in Table 4, Table 5, and Figure 4. The data presented shows that interface quality has a positive trend, higher than usability and information quality, both in maximum value and average results. These values indicate that, when using Build 3D, students perceive high quality in the application's interfaces. The quality of information presented in Build 3D achieved the second best results, with a maximum value of 6.09 and an average of 5.54. This suggests that Build 3D is designed in a way that allows students to interact with it intuitively and without difficulty. Furthermore, if the application displays useful and interesting information, it is highly likely that students will adopt it and be motivated to use it for their learning. System usability showed the lowest score among the 4 categories, with a maximum value of 6.07 and an average of 5.8 experienced when using Build 3D could negatively affect users' confidence in the application. These results suggest that the application's design can and should be improved in terms of usability and ease of use to enhance students' perceptions. Finally, the overall satisfaction results indicate that Build 3D was adequately perceived by students, with scores ranging from 6.04 to 7.0, most scores being close to the mean of 6.54. with a standard deviation of 0.5, indicating some variability in 13 Guatemalan quetzals indicates that users found the information provided by Build 3D, whether in the form of on-screen messages, guidance, or additional documentation, was not entirely helpful in completing their tasks. This low score suggests a significant deficiency in terms of the support provided to users for effectively using the application. Addressing this issue by improving the quality, visibility, and relevance of information, as well as personalizing support, will be crucial to optimize user experience and learning effectiveness. On the other hand, question 6 Guatemalan quetzals. I feel comfortable using this system. And 16 Guatemalan quetzals, the interface of this system is pleasant, receive the highest ratings.
Yeah.
The high score in 6 Guatemalan quetzals shows that users feel a sense of familiarity when using the application. Additionally, the high rating in 16 Guatemalan quetzals suggests that users found the application interface particularly attractive and enjoyable.
Yeah.
The high ratings in these questions underscore the success of Build 3D's interface in providing a visually appealing and pleasant experience for users. This positive aspect of usability not only enhances overall satisfaction, but may also positively influence engagement and learning effectiveness. In terms of overall usability, the median value is 7, reflecting a generally favorable opinion of the system's usability. However, it is important to note that while scores are consistent, some users may have experienced minor challenges in terms of ease of use or task execution efficiency. Additionally, it should be considered that using AR glasses suggests additional physical effort, which was evident in this research, and should be considered when deploying MR technologies in the classroom. B. Objective 2. 1. Perceived usefulness students. Most students gave a high score to the question about whether the application is applicable in classrooms to motivate learning about PC and smartphone hardware. This suggests a positive perception regarding the motivational impact of the application. Furthermore, the score related to learning improvement also tends to be in a high range, reinforcing the idea that students consider Build 3D useful for their education. Questions related to the perception of the application as an interesting tool and its applicability in the classroom also show consistent responses in the 4 to 5 range. This indicates that students find the application offers an interesting view of PC and smartphone parts and would be willing to use it in the classroom. Most students also consider the application an effective tool for guided learning and would recommend its use as an educational tool. The high average values in survey responses reflect a strong acceptance of the application as a teaching aid. In the question where students were asked to choose words that describe their perception of the application, the most common responses were easy to use and useful. This highlights that students value the simplicity of the interface and the practical utility of the application. Additional responses such as friendly, motivating, and entertaining also appeared, suggesting that the application has a positive impact not only on learning but also on the user experience. When reviewing the data by gender, no significant differences were observed between the responses of men and women, indicating that the application is perceived similarly by both genders.
Yeah.
However, some male students gave slightly higher scores regarding the perception of the application as entertaining, while female students placed more emphasis on the application being useful. Build 3D appears to be well received by students, who consider it enhances their learning and is applicable in an educational setting. Ease of use and utility are the most highlighted aspects, while entertainment and motivational elements also play an important role in the user experience. Sixth conclusion. One of the key advantages of using the IBM-CSUQ was its ease of implementation, as it allowed for the rapid and systematic collection of quantitative data. Another advantage or reason for using it should be that it is a mature instrument that has been widely validated by numerous studies. Additionally, the tool facilitated result analysis by providing a clear 1 to -7 scale for each item, enabling a detailed analysis of standard deviation and averages across different countries. This resulted in robust data supporting conclusions about the system's usability and acceptance. The analysis of the 4 key factors for the Build 3D application reveals positive acceptance among students. This analysis suggests that the application is well received, but also identifies areas where student perception could be improved. Enhancements in these areas could help reduce variability in user experiences and further increase overall acceptance of the application. The results show that Build 3D is perceived by students as a useful and efficient tool for teaching PC and smartphone hardware. Students highlighted the ease of use, the ability to become productive quickly, and the application's effectiveness in completing educational tasks. Although overall satisfaction is high, areas such as the clarity of error messages and access to certain information could benefit from improvements. In general, students recommend the application as an effective and valuable educational tool for practical hardware learning, and they appreciate its interface for its simplicity and functionality. The research reveals that students perceive Build 3D as a useful and effective tool for supporting PC and smartphone hardware education. High scores in application recommendation, perceived usefulness, and learning improvement indicate that students consider the application to have a positive impact on their education. Furthermore, ease of use is a highly appreciated feature, ensuring that the application is not only pedagogically effective, but also accessible and user-friendly. Although motivation and interest could be slightly improved, the overall perception supports the conclusion that Build 3D is a recommended tool among students, and has significant potential for continued implementation in educational institutions.
Yeah.
7th, future work. Currently, this research focuses on a group of students with similar demographic characteristics. Future work could include students from different educational levels, or even different fields of study to explore the effectiveness of using MR technology in other educational contexts. It would also be interesting to conduct comparisons between different educational institutions, both nationally and internationally, to verify if the perceived utility of the application is consistent or varies depending on the region and the technological resources available in each educational environment. Additionally, a longitudinal study could analyze whether students who use Build 3D retain the acquired knowledge better over time, compared to traditional methods. This would involve a multi-phase evaluation, where students would be assessed again months after using the application to determine if it has a positive effect on long-term memory and the transfer of skills to real-world applications. Furthermore, it could be analyzed if students are able to transfer the knowledge acquired through Build 3D to problem-solving in real-life scenarios, such as the physical assembly of hardware. This could include conducting practical assessments in labs with real equipment. Based on the feedback gathered in this research, the interface and usability of Build 3D could be improved, especially in areas where students identified opportunities for enhancement, such as information presentation and error message clarity. Future work could involve developing and testing a new version of the application with specific improvements and comparing the user experience before and after these changes. Another potential avenue for future work could explore the integration of artificial intelligence to further enhance the learning experience. For instance, AI could adapt to the individual needs of each student, providing real-time personalized feedback. References.
Okay. Now you can read all the references that are given here. So the paper is almost now over. Okay. Now what I can do, you can read, you can check out all these references. Okay. Now I'm going to starting from here. The authors are going to read it. Okay.
Santiago Criollo C. was born in Quito, Ecuador, in 1984. He received the BS degree in Electronics and Information Networks Engineering from the National Polytechnic School,
That's good.
Quito. In 2010, the MS degree in Communication Networks from the Pontificia Universidad Católica del Ecuador, and the PhD degree in Computer Science from the University of Alicante, Spain, in where he has oriented his research to the use of mobile devices as support. In higher education. Since 2013, he has been a professor of information technology with Universidad de las Américas, Quito, Ecuador. Andrea Guerrero Arias was born in Quito in 1985. She received the English language from the Army Polytechnic School and visual communication from the Universidad Autónoma de Quito, and the BS degree in teaching English from the University of La Rioja, Spain in 2022, is interested in researching the use of mobile devices in educational enhancement. She has been a professor of EFL with the Jezreel International Christian Academy, Quito, Ecuador. Agariadne Dwingo Samala received the degree from the Department of Computer Engineering, Faculty of Information Technology, Universitas Andalas, Indonesia, the Master's degree in Technology and Vocational Education from the Faculty of Engineering, Universitas Negeri Padang in 2015, in 2023, with a research focus on the convergence of technology and education. He is currently a professional educator, a futurologist, a dedicated researcher, and an assistant professor with the Faculty of Engineering UNP, specializing in informatics and computer engineering education. He is an external collaborator with the Digital Society Laboratory, Institute for Philosophy and Social Theory, University of Belgrade, Serbia. In addition, he is a member of the International Society for Engineering Pedagogy, Austria. With a deep passion for education, he has conducted impactful research on technology-enhanced learning, emerging technologies in education, flexible learning, 21st century learning, and technology vocational education and training. Unifa Miftakul Arif received the diploma degree from the Department of Electronics Engineering, Polytechnic Elektronika Negeri Surabaya, Indonesia, in 2007, and the master's and PhD degrees from the Department of Electrical Engineering, Institut Teknologi 10 November, Surabaya, Indonesia, in 2010 and 2010. He was an assistant professor with the Department of Informatics Engineering, Universitas Islam Negeri Maulana Malik Ibrahim, Malang. His research interests include game technology, learning technology, metaverse, recommender systems, blockchain technology, and the Internet of Things. He is a member of IEEE. He is also active in managing international journals as an editor or a reviewer. Sergio Lujan Mora was born in Alicante, Spain, in 1974. He received the degree in Computer Science and Engineering in 1998 and Computer Engineering from the Department of Software and Computing Systems, University of Alicante, in 2005. He is currently a senior lecturer with the Department of Software and Computing Systems, University of Alicante. He is the author of several books and many published papers in various conferences and high-impact journals. His main research interests include web applications, web development, and web accessibility and usability. In recent years, he has focused on e-learning, massive open online courses, open educational resources, and the accessibility of video games.
Okay, fine. Now I'm going to summarize it. Okay, going to read the summary now.
Research summary: Advancing hardware education via mixed reality. 1. Context and problem statement. Educational gap. Current pedagogical methods for teaching PC and smartphone hardware assembly lack immersive, hands-on experiences, particularly in settings constrained by limited physical resources. Proposed solution: the researchers developed Build 3D, a mixed reality application utilizing the MetaQuest 3 headset, designed to simulate hardware assembly processes in a virtual environment. Research objectives: the primary goals included assessing students' usability perceptions and identifying the tool's perceived utility as a support for practical engineering education. Development and methodology. Application design Build 3D was created to allow intuitive manipulation of components, such as motherboards and cameras, using hand gestures like grabbing and releasing, monitored by the headset's internal cameras. Key functionality: spatial awareness. The app uses 3D object detection to trigger specific user actions and a text tracking system to ensure that technical information remains readable. Holographic guidance. A system of visual hints and collision validation ensures that hardware is assembled correctly, reducing cognitive load for novices. Usability evaluation. The study employed the IBM-CSUQ, involving 50% higher education students who spent 20 minutes engaging with the application. 3. Analysis of findings. Usability dimensions. Interface quality rated the highest among categories, suggesting the user interface was visually appealing and pleasant to navigate. Information quality achieved the second highest score. However, some users noted that specific on-screen messages could be clearer to enhance task efficiency. System usability scored lowest among the evaluated dimensions, indicating potential areas for design refinement to simplify the overall interaction experience. Perceived utility. Participants overwhelmingly described the app as useful and easy to use, indicating high potential for classroom integration and student motivation. Gender perspectives. Analysis revealed consistent results across genders, with no significant differences in how male and female students evaluated the application's effectiveness. Conclusions and future directions. Overall impact: Build 3D proved to be a highly effective educational tool that successfully minimizes the risks associated with handling expensive physical components, while simultaneously increasing student engagement. Refinement needs. Future updates will focus on improving the clarity of instructional text and feedback mechanisms to further optimize the learning experience. Expansion goals. Ongoing research will explore the longitudinal impact of MR on knowledge retention, compare performance across diverse demographic groups, and potentially integrate artificial intelligence for personalized student feedback. This research demonstrates that mixed reality, specifically via the MetaQuest 3, provides a robust, scalable alternative to traditional hardware labs. By achieving high user satisfaction scores in usability and utility, Build 3D establishes a clear pathway for integrating immersive technologies into modern engineering curricula to enhance student skill acquisition and practical confidence.
Yeah, that's very good. So it's time to practice some questions, make some questions, and practice it. So number of questions, 10 is okay, or 15. Start from 10 and then go 15. What's your 15 or 20? Select pages. You can select pages also. You can make questions. You can use this tool, Speechify, for making and questions and for summarizing and making podcasts as well. You can make podcasts as well. Okay. You can ask question and many things you can do. Okay. 15. Questions are generating, questions are generating, questions are generating. Almost done. Training, hmm, teaching, teaching. Which has a river use? Metacustry, computer system usability questionnaire. Okay. Usability evolution, interface quality, information quality, system usability. That's great. 50. Three usability dimensions is the highest. Which of the three usability dimensions is the first? Rating. Overall satisfaction. No, 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 no. Interface quality. What methodology was employed to develop build 3D application? Yes. How long did it take? 10 minutes, 10 minutes. Which of the following describes a key advantage of MR mentioned in the text? Confidence, okay? Security approach, learning without fear of damage. To change, register, to call for precision. This was really to restart the assembly for us to call for help. Really.
What is the primary function of the red button in the Build 3D?
Application. To switch between, okay. Which is,
Which specific question from the IBM-CSUQ received the lowest score?
easy to understand, okay.
What was the gender breakdown of the participants? What is a identified limitation of using Mr. in education?
This is not effect
What is the primary benefit of using holograms in Build?
and build 3D, okay.
Which of these words was most commonly chosen by students to describe Build 3?
Useful and easy to use. Okay, 73% is really great. You can see the quiz. Interface quality was correct. 10 minutes is correct. And to switch between the red button was used to no restart the assembly process, but to switch between smartphone and PC visualization. This is what it. This one is easy to understand. Then again you can generate new questions. If you click generate new questions, again you will get new questions. Suppose I can generate again new questions will frame. So you can practice again and again new questions after reading the paper. You can summarize it. You can make questions. Then you answer it by yourself
What
for
is the
checking
primary
your
function of the Build 3D?
understanding. This process you can repeat many times till you not able to understand the paper very clearly. Okay. What is the primary function of the build 3D application? So again, the same questions are coming.
Which hardware device is used?
You can give the answer like this.
Which survey tool was used to measure the usability of Build? Which dimension of usability received the highest rating in the study?
This is again intercoil. Again, answer correct. Incorrect. Intercoil.
What methodology was used for the software development of Build 3D?
Scrum. You can give the answers.
Which of the following was identified as a limitation of Mr. in the classroom?
Ability to work. Lack of difficulty in understanding. What's it considered? A limitation of eyesight. Yeah.
What is the primary way users interact with objects in Build?
Daring realism.
What does the red button feature in Build 3D represent?
That's all also already. So it is repeated
How many students participated in the usability evaluation?
again.
What was the lowest scoring specific question in the IBM-CSUQ survey?
Cleanliness of interface was great. Comfort using the system was great. Clarity on the screen documentation. Age of learning the system. Age of learning was great. Agent of. No, this was okay. Fine. Only one was correct. So 90% correct. Practice as much as you can, and you will get the perfect understanding of the paper. Okay. And you can also chat with it. You can ask questions related to this paper. You can ask like I am asking. You can also talk with it. Allow it. Okay. You have to allow. Who are the authors of this paper?
The authors of this paper are Santiago Criollo C., Andrea Guerrero Arias, Agariadne Dwingo Samala, Unifa Miftachularif, and Sergio Lujan Mora. If you'd like more details about any of them or the paper's content, let me know.
Yeah. Provide some detail about each author.
Here's a brief background on each of the authors. Santiago Criollo C. is a senior member of IEEE, originally from Ecuador, with expertise in electronics and computer networks. Andrea Guerrero Arias also comes from Ecuador with a background in linguistics and visual communication, and she's interested in mobile devices and education. Agariadne Dwingo Samala from Indonesia has expertise in technology and vocational education. Unifa Miftachularif, also from Indonesia, has a background in electronics engineering and focuses on learning technologies in the metaverse. Finally, Sergio Lujan Mora from Spain is a senior lecturer at the
Yes.
University of Alicante, with notable contributions to web development and e-learning.
Okay. Thank you so much.
You're welcome. If you have any more questions or need further details, feel free to ask. I'm here to help.
Can you summarize the paper in few lines?
This paper explores the use of mixed reality technologies with MetaQuest 3 to teach PC and smartphone hardware assembly. It introduces the Build 3D application, providing an immersive hands-on learning tool. The usability was evaluated using the IBM-CSUQ survey, showing high user satisfaction. The findings suggest that the application effectively supports educational goals by enhancing
Anything? Okay. Thank you so much. देखो, you can use this tool very effectively to understand the paper, to summarize, make questions, and understand it more and more. Okay. You can also I use AI chat, AI use summary, I use quiz. I these three things I've already used. Let's try podcast. So for postcard, you can select which type of thoughtful talk you want to do, lecture talk you want to do, storytelling you want to do, late night. So I selecting thoughtful talk. Okay, and which language you are comfortable in. English, India. Suppose I select this language. Okay, and try asking. You can ask any question you want to. Just make the market report, explain it for investor. Okay, you can ask questions. Okay, uh, discuss about the if you and great. And then it will create. Just command it and it will generating podcast. One over the studio. Reading your document, it will read the document and as well to find the
The
title, perfect
fundamental
title.
challenge of teaching complex hardware assembly, like that of a PC or smartphone, is often the sheer cost and logistical nightmare of physical labs. Yet, a new mixed reality application called Build_3D, experienced through the MetaQuest 3 headset, promises to eliminate these barriers entirely.
It's cool.
Malik, this paper, Enhancing the Educational Model Using Mixed Reality Technologies with MetaQuest 3 by Santiago Criollo C. and his colleagues, proposes a fascinating solution. What is the core problem it aims to solve in today's educational landscape?
Elliot, the core issue is the significant lack of effective digital tools for hands-on teaching, particularly for PC and smartphone hardware assembly. This is crucial because practical learning is vital for engineering students and those in related fields. Traditional methods like simulators or online tutorials just haven't delivered that immersive, efficient experience needed for truly understanding hardware.
That's cool.
That's why Build 3D was developed. It's a mixed reality application specifically for learning hardware assembly, designed to run on the MetaQuest 3 headset.
Yeah.
So, Build 3D is essentially creating a virtual hardware lab For those unfamiliar, can you explain what exactly mixed reality is and how it differs from, say, virtual reality or augmented reality?
Certainly, mixed reality, or MR, combines the best of both virtual reality and augmented reality. VR creates a completely immersive, digitally generated world, while AR overlays digital information onto your real physical environment. MR merges these two, allowing users to interact with both virtual and physical objects seamlessly in a unified
Unified
environment.
environment.
Think of
Yeah.
it as a virtual motherboard floating on your actual desk.
This technology has grown significantly due to advances in graphics processing, lighter devices, and natural interaction systems like eye tracking and gesture recognition.
That makes sense. It's not just about seeing virtual objects then, but interacting with them as if they're real. The paper points out MR's potential in engineering education, saying it allows students to interact with virtual models of complex equipment. How does this benefit students, and what were the main challenges Build 3D had to overcome in its design?
The benefits are immense. It reduces the need for expensive physical components and minimizes the risk of damaging costly equipment, which is a big concern in traditional hardware labs. Students can experiment freely without fear of breaking anything, fostering a more confident exploratory learning approach. It also allows them to repeat complex procedures as many times as needed, which isn't always possible in a physical lab. In designing Build 3D, the team faced two main challenges. First, creating a natural assembly process for components, and second, designing an intuitive interface. They focused on natural interactions, meaning users manipulate virtual objects using hand gestures like grabbing and releasing, mirroring real-life actions. This was achieved by leveraging the MetaQuest 3's cameras to detect finger positions and movements.
So the interaction feels very natural, almost like you're holding the components. And what about the information aspects? How does Build 3D provide technical details to students?
The application includes spatial text, a feature that displays detailed information about each component. This text functions as a 3D object that users can move around. Crucially, they implemented a text tracking system so the information always stays legible and aligned to the user's view, even if they move or rotate the component. This avoids the frustration of text appearing at an awkward angle or becoming invisible. Visually, the application allows students to disassemble PCs and smartphones, showing internal elements like batteries, motherboards, and camera modules. Information panels explain the purpose and characteristics of each part. It's also scalable, meaning it can be extended to teach assembly for other types of hardware. And there's a red button to switch between smartphone and PC views.
That's cool.
That's very comprehensive. But developing an application like this is one thing. Understanding if it actually works for students is another. How did Creolosi and his team evaluate Build 3D's effectiveness?
They conducted a usability analysis using the Computer System Usability Questionnaire, or IBM-CSUQ, which is a widely accepted standard. 50 students from a higher education institution participated. Each student spent about 10 minutes assembling a PC and another 10 minutes assembling a smartphone using Build 3D, then completed the questionnaire.
The IBM-CSUQ focuses on three key dimensions: interface quality, or interqual,
Interqual.
information quality, or infoqual,
Infoqual.
and system
System
usability,
usability.
or SysUse.
SysUse.
There's also an overall satisfaction component. The results were quite positive, showing high user satisfaction across the board.
High user satisfaction is a great outcome. Could you elaborate on the specific findings for those three dimensions? And were there any particular areas where the application excelled or where it still needed improvement?
Absolutely. The interface quality, interqual, was rated the highest, showing that students found Build 3D's interface pleasant and attractive. Information quality, infoqual, came in second, suggesting the information provided was generally useful and helped them complete tasks. System usability, SysUse, scored the lowest among the three main categories, though still reflecting a generally positive perception.
Delving deeper, two questions received the highest ratings. Quote, I feel comfortable using this system, end quote, and quote, the interface of this system is pleasant, end quote. This indicates a strong sense of familiarity and an enjoyable visual experience. However, the lowest score was for the question, quote, the information provided with this system is easy to understand, end quote. This suggests that while information was present, its clarity, visibility, or relevance could be improved to better support students.
That's an interesting tension. The interface is pleasant and comfortable to use, but the clarity of the information itself could be better. So while the experience feels good, perhaps some of the instructional text might be overwhelming or not immediately helpful. What about the perceived usefulness of Build 3D? Did students feel it genuinely helped their learning?
Yes, overwhelmingly so. Most students, regardless of gender, gave high scores to questions about whether the application was applicable in classrooms to motivate learning, and if it offered an interesting insight into PC and smartphone parts. They also indicated they would use it in their classrooms and that it improved their learning.
Yeah,
When asked to describe the application in their own words, the most common responses were easy to use and useful, followed by friendly, motivating, and entertaining.
entertaining.
This really underscores that students value both its practicality and the positive experience it provides. The study found no significant differences in perception between male and female students, which is also noteworthy.
So Build 3D largely delivers on its promise then, an immersive, effective, and well-received tool for teaching hardware assembly, especially where physical resources are scarce. What are the key takeaways from this research by Criollo C. et al., and what's next for Build 3D?
The research firmly concludes that Build 3D is perceived by students as a useful and efficient tool for teaching PC and smartphone hardware. Its ease of use and ability to make students productive quickly were highly appreciated. Despite the positive overall satisfaction, the clarity of error messages and access to certain information are areas identified for improvement. For future work, the team plans to expand studies to different educational levels and fields, conduct international comparisons, and even perform longitudinal studies to see how knowledge retention holds up over time compared to traditional methods. There's also the exciting prospect of integrating artificial intelligence to provide personalized real-time feedback to students, further enhancing the learning experience.
This paper highlights how mixed reality can address real-world educational challenges. If you found this discussion insightful, consider sharing this episode with someone who might benefit from it.
Yeah. So you can create your podcast. Now I created a podcast of the paper. So you can do the same thing and understand the paper that you are reading or the any book, any chapter you are reading of any book. You can just summarize it, make a podcast, make quizzes, learn as much you can. Okay. Thank you so much. For now, it's time to end this video. Okay. Thank you so much for having such a nice research paper reading and listening this discussion last postcard discussion. Thank you so much. Okay.